Hello everyone, this is lecture 11 of course PE 645. In the previous lecture, we have dealt with oversampling and feature selection, and we understood the meaning of oversampling, which is increasing the number of minority class instances to be equal to the majority class instances. So if you have two classes, one with 100 and one with 200 instances, so we are incrementing and increasing the number of instances of the 100 class to 200 class. And undersampling is the opposite. We are removing the redundant features or removing the unrelated irrelevant features from the majority class to be equal to the number of instances to the minority class. Feature selection is a process of selecting the most promising features that can produce and report the highest performance. And this can be done using different techniques such as rubber methods and filter methods. Both of them can help enhance the performance of a machine learning model, and it is not necessary to use all of these techniques to enhance the performance. We are trying a technique. If the performance is enhanced, then we can keep this technique to be used with this machine learning system. If not, we can try another technique, and so on. The third approach to enhance the performance is feature normalization. And feature normalization is a crucial pre-processing step in machine learning to ensure that all features contribute equally to the model. And this will avoid bias towards features with larger magnitudes. So, for example, you can open a set of features, and when you read a specific feature column and read another feature column, you can notice that some features got smaller values and some features got higher values. For example, the mean value can reach up to, for example, 500, while the kurtosis can be smaller floating numbers. And this gap in the magnitudes may in somehow introduce bias in the system. So feature normalization helps to eliminate that. And this can also get better performance and convergence of the machine learning algorithms. There are many techniques to be used with the feature normalization. Each of them has its own advantage. The first one is called standardization. And standardization technique standardizes the features by removing the mean and scaling to the unit variance. And standardization assumes that the data follows a Gaussian distribution. So after scaling and normalizing this feature, it will get a mean of 0 and a standard deviation of 1. To accomplish that, we are subtracting the mean value from each feature and dividing it by the standard deviation. Another technique is called min-max scaling, and the min-max scaling scales and translates each feature individually to be set between 0 and 1. And it's useful for algorithms that don't assume any particular distribution of the data and can be sensitive to outliers, as it scales all data to the same range regardless of their initial distribution. And this can be accomplished by subtracting the min value, which is the lowest value, from each feature and dividing that by the difference between the maximum value and minimum value. A third feature normalization technique is called robust scaler, and it's designed to be robust to outliers by using the median and interquartile range for scaling, rather than using the mean and standard deviation. So instead of subtracting the mean, we are subtracting the median, and instead of dividing by the standard deviation, we are dividing by the interquartile range. And it's useful when the data contains outliers, as it reduces the influence on the scaling process, ensuring that all features are scaled in a way that is more representative of the majority of the data. And the interquartile range can be calculated by subtracting 75th percentile minus 25th percentile. Another technique is called normalization, and the normalization normalizes the data to have a specific norm value. There are three techniques: L1 normalization, L2 normalization, and max normalization. And L1 normalization scales the data such that the sum of the absolute values of the features equals 1, which can be useful for sparse data. And this can be accomplished by dividing each feature by the summation of the absolute values. L2 normalization scales the data such that the sum of the squares of the features equals 1, making it useful for data where the Euclidean distance is important. And this can be accomplished by dividing by the square root of the summation of the squares of each feature. Max normalization scales the data by the maximum absolute value, ensuring that the maximum value of each feature is 1, and this can be accomplished by dividing by the maximum value in the feature. Normalization can be performed feature-wise or instance-wise, and this means if we have a set of features and set of instances, which are the rows, is that we can apply each normalization technique on the instance itself, or we can apply it on the feature itself. And the commonly used approach is that we are applying on each feature so that each feature can be inside the same range. There is another approach called hyperparameters optimization, and we need to distinguish between parameters and hyperparameters. In machine learning, parameters reflect the weights and coefficients of the machine learning model. For example, in linear regression, we are trying to fit a set of data using, for example, a line, if we are calling linear regression, and this line has an equation of y equals ax plus p, and a and p are modified and updated in each iteration during the training process to fit the data and score the least error. These coefficients or weights are called parameters, and there are many techniques such as gradient descent to optimize these parameters. But hyperparameters, these are the configurations involved in the learning process outside fitting the line in this linear regression problem. And this can be, for example, which normalization technique, which oversampling technique, which undersampling technique, which feature selection technique. By getting a range and selecting a specific value from this range, for example, we have many normalization techniques such as L1, L2, max, robust, standardization, and so on. This is a range, so we need to select the most promising of them that can get the highest performance for our data. By doing that process, this is called hyperparameters optimization, and hence hyperparameter optimization is a critical step in machine learning workflow, and it involves the selection of the most effective hyperparameters or configurations to improve the performance of a model. Hyperparameters are the parameters or configurations that are not learned. So in our example here, A and B are trainable or learnable parameters. So they are not hyperparameters. But the hyperparameters are which technique, which approach, which model to be used to get the highest performance. So hyperparameters are not trainable or learnable, but are set prior to the training process, such as the learning rate, number of layers if we are dealing with neural network, or the number of trees in a random forest, and so on. By tuning these hyperparameters, we can improve and enhance the efficiency and accuracy of the model. There are many techniques to be used for hyperparameter optimization, such as grid search. And the grid search here involves specifying a grid of hyperparameter values and exhaustively trying all possible combinations. It's very simple and effective to be applied, And we have applied that in the previous lecture manually by setting a set of 4 loops together, cascaded to each other, one for which model, one for which oversampling technique, and one for which technique in the feature selection. And this can be computationally expensive and time consuming, especially with a large number of hyperparameters. Imagine that we have 10 models, we have 10 normalization techniques, and 5 oversampling techniques. So by doing that using grid search, we are trying all combinations, and these combinations will be 500. Imagine that we added another hyperparameter with also 10 hyperparameters, 10 values in its range, so the combinations will be 5000. By increasing the number of hyperparameters that we are tuning, this approach will be computationally expensive and time consuming. So we need to try better approaches. Another approach called random search. Instead of trying every combination, random search randomly samples from the hyperparameter space. So it can pick random combinations and leave others. This approach can be more efficient than grid search, particularly when only a small subset of hyperparameters significantly impacts the model performance. So instead of picking all of these combinations, we are picking from the 5000, we are picking only 100 random combinations. Bayesian optimization is a third technique, and it builds a probabilistic model of the objective function and uses it to select the most promising hyperparameters to evaluate in the next step. And Bayesian optimization can find the optimal or near optimal hyperparameters with fewer evaluations compared to grid search and random search. So if we have a smaller number of hyperparameters and smaller ranges, we can use grid search or random search. But if we have huge number of hyperparameters and their ranges are considered as a large number, we can use Bayesian optimization. More techniques, gradient-based optimization, and this technique applies gradient descent or its variant to optimize the hyperparameters. It's commonly used for tuning hyperparameters of differentiable models, but is less common for discrete hyperparameter spaces. So if we have discrete number of instances, for example, for oversampling technique, we cannot use the gradient descent or gradient-based optimization. Evolutionary algorithms and the use mechanisms inspired by biological evaluation, such as selection, mutation, and crossover, for example, using the genetic algorithms to evolve hyperparameters over successive generations. There are many studies and projects built on using evolutionary algorithms for the hyperparameter tuning. After understanding that there are many number of approaches to optimize the hyperparameters and its usefulness in getting high performance, there are many frameworks that can be used for hyperparameter optimization, such as Optuna. And Optuna is a powerful and flexible framework for hyperparameter optimization that has gained popularity for its efficiency and ease of use. It's an automatic hyperparameter optimization software framework, and it's designed to be easy to use and efficient. It uses an adaptive sampling algorithm utilizing the state-of-the-art techniques such as the Bayesian optimization that we have discussed to explore the hyperparameter space. After understanding through the lectures that we need to extract features and apply machine learning with some techniques to optimize the performance, we can summarize all of that in this workflow. First, we are loading the dataset, and this dataset can come from different platforms and places. So we can get a public dataset from, for example, Kaggle, IEEE Dataport, and many others. And this public data can be in the form of images or frames, or can be on the form of a ready Excel file or CSV file that contains the features. So when we got data with images such as the lung or breast cancers, we had to apply ROI extraction based on the mask if it exists. So instead of focusing on all of the image, we are only focusing on a small part which is related to the cancer or the condition for this patient. Then we applied some processing on this image to only remove the bounding black pixels or bounding areas to only get the cropped ROI that contains the tumor or cancer. And after that, we applied a set of features which is called handcrafted features, such as first order features, GLCM and GLRLM. We also applied LPP, and by extracting the LPP matrix, which is called the local binary pattern, whether by using the original technique or the uniform technique, we then applied using this matrix handcrafted extracted features again, so we could have two versions, one using the original ROI and another using the local binary pattern matrix. And all of these features are then stored in a CSV file or a file that can be used later in our machine learning. So this whole process is called handcrafted features extraction. Also, when we notice that some data didn't got masks, we applied the feature extraction on the whole image. So we bypassed this step and that step. By doing all of that, we finally got a dataset. So the first step in building and tuning a machine learning based system using handcrafted features is to load the dataset. And after loading the dataset, we split it into training and testing. And if you are using models or techniques such as deep learning or artificial neural network or deep neural network, you can split the data into training, testing, and validation, because in the training process, they will require training and validation. And finally, after the training process completes, you are applying the testing subset. Using this or that, you are splitting the data. After that, we are encoding the data splits using the label encoder or any encoder to convert from using classes in a string format to numbers, because we will later use these numbers to calculate the confusion matrix, and to calculate the confusion matrix you need numbers. Then you are defining an objective function, and this objective function, which is outlined here, will get the hyperparameters and will report a performance measure. So assume that is a black box, that it accepts the data or the splits and accepts the hyperparameters, and then it produces an output, which is a numeric value that reflects the performance. So before getting inside this black box, let's move to the right. We mentioned we need a hyperparameter or a combination of hyperparameters. So we are creating the space of the hyperparameters. We are saying, for example, we have these machine learning models, these oversampling techniques, these normalization techniques, and so on. And this is called the space that we need to search into. And then we are defining a study. And this study will accept two things and produce the best hyperparameters that reflect the best performance. It accepts the space and the objective function. What's done inside this study, for example, if you are using the Optona framework for hyperparameter optimization, in this study, it will get the combinations, and for each combination, it will execute the objective function, which is the black box here, and it will receive then the output, which is the performance. So, for example, in this study, it will say, for these combinations, I got that performance. For this combination, I got this performance, and so on. And finally, after its completion, it will report that these hyperparameters got the best performance, so you can use them. So the study will report the best hyperparameters, which will get the best performance. So what is inside the objective function? What you are building in this objective function depends on the hyperparameters. So if you are tuning the normalization techniques, then you need to apply internally normalization techniques based on the selected value from the range of normalization techniques. And the same for feature selection and oversampling. So the traditional approach is to get the trial hyperparameters, then sample the train subset, and we are only oversampling or undersampling the training subset. Then we are normalizing the data splits. You are normalizing the train split individually and the testing split individually. Then we are applying feature selection to select the most promising features. Then based on the oversampled, normalized, and selected features, we are training and evaluating the machine learning model. After that, we are calculating the performance metrics and getting, for example, an average insight or an average value from the performance. Then we are reporting the objective function value, which will be returned later to the study, which will be set here to select which is the highest. So we need to implement that. So here we imported Optuna, and this can be installed using pip command, pip install Optuna. And Optuna internally may require these configurations, so you need to add it before importing Optuna. And this is related to the number of threads to avoid any warnings and errors during the execution. Then we imported NumPy and pandas and imported the different modules related to the models, feature selection, the metrics, the preprocessing, oversampling, and undersampling. And then we set these lines to avoid any warning. So instead of retrieving a warning, we are saying that only verbose and report the errors and ignore any warnings. We built two functions, one for the multi-class classification and one for the binary classification. And we need again to mention that we added epsilon value to the denominator to avoid any division by 0. Then we created a function to load the dataset, and it accepts the file path, and if we need to fill a value, so we are passing the fill value, it loads the dataset, shuffles it, and fill the empty or null cells with the fill value, which is default by 0. Then we are getting the features and the classes X and Y, and then we are printing some information on the command window. After that, we are returning X, Y, features columns, and target columns. We have created another function as an encoder, and this will accept the Y, which contains string values, and encode the values. And we got a condition here if we need to transform only or fit and transform. So the label encoder or the encoder, which is provided by the scikit-learn, contains two functions, fit transform and transform. The fit transform will teach the encoder that the string label has a corresponding integer label of 0, and the second will be for 1, and so on. After getting a dictionary or a table with which string reflects which integer or encoded value, it then transforms the whole column of labels. But the transform only transforms without rebuilding the encoder. So we first will use the fit transform and then transform. We will use the fit transform with the training and then use the transform with the testing. After that, we build another function called normalize data. It will accept xtrain, xtest, and the technique, and then we have a dictionary of the techniques. After that, it will normalize training and testing, and if there is no technique passed, we will return the original data. If the technique starts with normalize, and we will illustrate that after a bit, it will normalize each of them, the training and testing, individually, and otherwise, which here means standardization until we reach robust scalar, we are getting the object from the dictionary, fit transform the training data, and only transform the testing data. So what is the difference here? We understood the meaning of each of them, and inside the scikit-learn, all of these techniques are applied on the features columns. However, the normalized technique applies in the instance row. So instead of doing like that, normalize, which is a technique, and say here normalizer, we are building using another function called normalize. As mentioned, this function applies on the instances and we don't need that. So we used another function in the scikit-learn called normalize that accepts the feature or the instance or whatever, and it accepts the technique. And which axis do you need to normalize? You need to normalize the rows or the columns. And here we applied both of them. So instead of only applying on the instances, we are applying all combinations from L1 to max. And we applied on the features and the rows. Then we created a function called train evaluate the model. Here we built the dictionary of the models, and based on the model string, it will access the dictionary and get the model. Then it will set the hyperparameters. It will fit the model using the training data and evaluate it using the testing data and compute the confusion matrix and report them. And here it checks first if we are dealing with binary or multi-class classification. We also build a function called feature selection, and here instead of selecting the feature based on the chi-square or ANOVA, we here applied randomization. So in each call to this function, it will get a random set of features and ignore others. After getting the random set of features, we are selecting the modified train and testing subsets and returning them. And NP random choice, we are passing here what is the range, what is the length. So if you have 5 features, it will produce 5 binary values, 0 or 1 for each feature. And it may produce all of them are zeros, which means ignore all of the features, and this is not reasonable. So if the sum of this vector is 0, select or pick any random feature to be 1. After that, we are passing here this binary vector, and this binary vector, if it's 0, it will ignore that feature. If it's 1, this means keep this feature. Also, you can implement your own technique. There are wide range of techniques. You can apply it here by getting the training and testing and producing the updated training and testing. So whatever you are doing here, you need to report the new subsets. Then we created a function for sample dataset for oversampling and undersampling techniques, as we illustrated in the previous lecture. Then if the technique is none or empty, we return the original data. If it's not, we are getting the object and fit resample it. And we are doing that only for the training. Then we built the objective function. Before getting inside the objective function, which is our black box, we are building the study using this function, train Optuna model. It accepts a set of parameters or configurations as a function, and it creates Optuna study that we need to maximize the objective function. And this is the study name, and this is the location of storing and logging the history. And the benefit and advantage of Optuna, if you halted or quitted the script after running, for example, 3 or 4 trials, you can load if exists. And if you set it to true and you defined the storage, it will load the study if it exists. So instead of starting from the first trial again, it will start it from what you ended in the last time. And here you are defining a sampler. You can define a random sampler, Bayesian sampler, or tree of Barzin sampler. You have many efficient optimization algorithms that you can find in this link. Here we use the TBE sampler from Optuna. Then we optimized the objective function for a set of trials, and we showed the progress bar to know the progress of our optimization, whether it's in halfway or it's near the end, and so on. And this objective function, we defined it here using lambda. We are passing the trial to the function which we said this is our black box. We passed xtrain xtest the lists of the hyperparameters, and this function should return an objective value that will be stored in this study or the optional study. After the optimization, we are storing the trials in a data frame, getting the best hyperparameters. Then we are storing the trials in a data frame, getting the best hyperparameters, storing the trials in a data frame, getting the best hyperparameters and the corresponding value, storing them in a CSV file, and then storing also the study objective in a pickle file. And here we are defining the different models. We are defining the hyperparameters for each model. For example, the decision tree, we are defining max steps, max features, and so on. And based on the version you are using with the scikit-learn, if you encountered an error that says you shouldn't use any value of those, you can remove it and try again. So then we define the different sampling techniques. We define the different normalization techniques. So what is inside this black box? It accepts, as mentioned, the trial, training, the lists, and it selects a model using the function suggest categorical. Here we are selecting the hyperparameters and storing it to be stored in the CSV and database. We got the sampling and normalization techniques, and all of that depends on the sampler that we are using. So if you are using random sampling, it will use a random value. But here we are using the TBE sampler, so internally it will manage which combination will be retrieved. Then we applied sampling, normalization, feature selection, training and evaluation, and got the objective value. And we put that in a try exception. So in any case that will cause an error, it will cause an exception, and then it will return an objective value of 0. So instead of causing an error and halting the application or the execution of the code, it will just accept and reduce an objective value of 0. Then we need to execute all of these functions. And here we applied on the mid-MNIST nodule 3D dataset, and you can change the paths on the dataset in hand you are using. Here we are defining the full path, training path, and prefix, and this prefix will be used later to store the pickle and CSV files as we mentioned. So if the training path doesn't exist, we will load the dataset from the full path and train split it and store the data into the training and testing. And in our example, we only got the training testing, but in other examples, you may only get the full path. So in our example, we will not need this portion, but I am keeping it here so it can be used with you later in any application. So you will only get the full path, and of course you will not find the training and testing. So this block will be executed as it will not find the training path. It will split into training and testing and store them. After that, it will load the training and testing and fill the values with zeros for empty cells. Then it will encode the data and execute the encode data function for training and testing, and then call the optional study for 3000 trials. By calling this function, which is here, it will create the study and then objective function and starts to optimize it. And after the optimization, it will store the results in CSV and pickle files. And as mentioned, we are prefixing it here before the postfix of each file, because if you are executing the code for multiple datasets, they will not overwrite each other. So you are defining a unique prefix for each trial or for each dataset. After executing the code and opening the CSV file, you will find that it reported the different configurations, and by sorting them in a descending order, you will find that the accuracy reached about 81.3 for the testing using normalization, bagging classifier, and these are the features. 1 means keep the feature, 0 mean drop this feature, and these are the hyperparameters, and this is the elapsed time for this trial if you need to compare the timing between the classifiers. So for example, here and here, this one reported higher performance than the second one, and it took less time than that one. And this, of course, may be a result from the feature selection and also the hyperparameters. So in this lecture, we have dealt and understood the meaning of feature normalization and hyperparameter tuning, and then we understood and implemented the workflow or a general workflow and the summarized version of a machine learning model, classification and hyperparameter tuning process and system using handcrafted features. And this can be done and applied using any hyperparameter tuning framework. And in our lecture and code, we used up to now for hyperparameter tuning, which is easy to use and popular for that purpose. Finally, when we reported the results and sorted them, we found that hyperparameter and hyperparameter tuning and feature selection increased the performance to 81 than the earlier results that we reported in the previous lecture.